All right, next I'd like to take a look at the different properties of our solar system. And so if we look up at the data projector, we can see this is a very famous picture. A lot of people have it on their t-shirts. It's called the Eagle Nebula. And so here's an example then of the shock waves. And at the points where the shock wave hits the gas, we have very bright regions. And so this is thought to be where new solar systems may be forming. And these dark regions could be places where the subregions are collapsing into a solar system in which we're not seeing the light that's coming from those little subregions. And so we think that within one of these subregions our solar system formed. You've seen this picture before with the ecliptic plane. The inner planets are in very close, the outer planets much farther away. In this next picture, and we also looked at this in an earlier lecture on sizes within the solar system. Notice that we have the inner planets, very small, dense, rocky, yet the outer planets very big, tend to be more like big, huge gas balls. Then we have the sun for scale here, so that you could fit 1,000,000 Earths inside the sun, but you could fit 1,000 Earths inside Jupiter. Okay, and so if we want to take a look then at not so scale view of our solar system, we'd have Mercury, Venus, Earth, and Mars. Now I'm putting them in a row here, just so that I can fit them on the board. And so these little inner rocky worlds, which many people believe are second generation planets, are what we call the inner planets. Okay, and so they are small, relatively speaking, or smaller. They are made of rocks and metals. They are fairly close together. And the reason for their small size, among other things, is that they're very close to the sun. So that the lighter gases, like hydrogen and helium, would be blown off of these inner worlds, leaving behind just these smaller worlds that are made of rocks and metals that are fairly close together. Then as we go into the outer solar system, we have Jupiter, Saturn. Now here I'm making them about the same distance apart. Of course, we know that that's not right. Uranus, Neptune. And we'll call Pluto a dwarf planet later. I won't include that in this description of the outer planets. So these are the outer planets, which in contrast are bigger, made more of sun-like material. By that I mean mostly hydrogen and helium. They're farther apart. And no solid surfaces. So you can't just land on one of these things the way you can on an inner planet. All the inner planets have solid surfaces. Okay, and so by the time that the sun's radiation gets to the outer solar system, the intensity of the light also obeys an inverse square law. Remember that we talked about the inverse square law before with gravity. How if you double your distance away from an object, you only feel 1/4 the gravitational force. Let's imagine that we're looking now at the sun, and the sun is like a big light bulb, okay? Now if I take a big light bulb or the sun and I move twice as far away, it's only going to be 1/4 as bright. And if I move 3 times farther away, only 1/9 as bright. 4 times farther away, 1/16 as bright. So by the time we get out to Jupiter, this is at about, as we saw before when we were looking at Kepler's laws, this is about 5.2 AU. By the time that we're 5 times farther out than the Earth's distance from the sun, remember this is not to scale, there's only 1/25 of the sunlight there. At Saturn, which is 10 AU, almost, for Saturn, that's only 1/100th the sunlight. For Uranus, at about 20 AU from the sun, you'd have only 1/400th the sunlight. And for Neptune, at 30 AU, only 1/900th as much sunlight. So from these great distances away, the sun would still be visible, of course, but it would just look like a glorified star. It wouldn't really be the kind of thing that you could warm your hands by. Hundreds of degrees below zero in these outer realms. And so these outer planets then can have more of the same kind of composition that the sun has, because the sun's radiation isn't powerful enough to evaporate off all the hydrogen and helium. Hydrogen and helium are very light gases. So the hydrogen and the helium were blown away from these inner worlds into the outer solar system, and this is one of the reasons why the inner planets are made just of rocks and metals and can still have solid surfaces. And so if you land on Jupiter, you just keep falling through. This has like a gaseous atmosphere, and then it has a smooth transition to a liquid interior. Over thousands of kilometers this would happen, and so there wouldn't be, even though there's liquid hydrogen and helium in the interiors of these outer worlds, the state of matter is quite a bit different than what we're used to, and you wouldn't have even a surface that you could float a boat on, because it would be like 50% liquid, 50% gas, and then you go down deeper, 75% liquid, 25% gas. Go down deeper, 90% liquid, 10% gas. And so there wouldn't be a well-defined surface that you could float a boat on, and it's not solid, so you certainly couldn't stand on it as having a solid surface. And so those are the big differences then between the inner and the outer planets. Of course, this had a lot to do with Jupiter's migration inward, which we think destroyed the first generation of inner planets and caused, from the debris that followed, a smaller group of inner planets to form. And this might be good for life too, because if we had formed as a bigger planet, like a big super Earth, we'd hold on to more of this hydrogen and helium. And so that would make and also the thickness of the atmosphere would tend to hold in heat and create a much bigger greenhouse effect. And so there are a lot of reasons why we think that super Earths might not be quite as conducive for the kinds of life that we have here on the Earth as smaller planets would be. And so it's like we won the lottery like 100 times in a row, that all of these things happen to work in just the right way for us to be able to exist here on the Earth. And even within these inner planets, you look at Mars, that's a desolate world. Venus is got temperatures between 600 and 900 degrees Fahrenheit. Mercury's got essentially no atmosphere. And so the Earth is the only one that just got it right in the inner solar system. Okay, so next, what I'd like to do is take a look at the inner planets, just individually. We'll go through and survey them. So if we look up at the data projector, we can take a look at the interiors of different objects in the inner solar system. Here is the Earth. Now the Earth has a core. That core is made out of mostly metals, for example, iron. The mantle is a rocky material made out of what are called silicates. Those are combinations of silicon and oxygen that kind of float up a little higher. The core is this more dense material, and then that's followed by this lighter mantle. If we look at the moon, though, what do we see here? Very little of the core material and a lot more of the mantle material. And so this is consistent with a moon that formed from that disk of the synestia, which was, we think, at that time, mostly the Earth's mantle material, and not so much of the core material of the Earth. In that early time, that core material would have sank in, the rocky material would have floated higher, and so the moon then would be made from a disk of material that was mostly mantle. And so that's consistent then with what we have observed by putting seismic instruments on the moon and listening for the shock waves from not moonquakes so much as from asteroids and comets that hit the surface of the moon. Mercury, on the other hand, has a large core and very little mantle. And so in Mercury's case, we believe, as I mentioned before, that Mercury struck either Venus or the Earth, or maybe some other object. We can't be sure it was Venus or the Earth, but those are the prime suspects. The Earth isn't admitting anything, but the Earth has been questioned, and so has Venus. But we think that Mercury had most of its mantle knocked off. So Mercury would have been a much bigger planet, but because its mantle was knocked off, it's mostly core in the interior and a much smaller planet. Okay, so if we look at Mercury in a little more detail, what we see is that Mercury looks more like the moon than any other planet does. When we take a look at some of the vital statistics for Mercury, its radius here, r, is about 1/3 the radius of the Earth. For the radius of the Earth is about 4,000 miles. Okay, so if you were to, let's say this is the Earth, you had Mercury like that, you could have 3 Mercuries fit across the Earth at the Earth's equator. But that doesn't mean that Mercury is 3 times smaller than the Earth in volume, because the volume goes like the cube of the radius. So the volume of Mercury is only 1/27, 1/3 to the 3rd power, the volume of the Earth. Okay, so it's a small world. Mercury is the Greek god for being very fleet of foot, and it has the fastest orbit around the sun. The period of orbit for Mercury is 88 days, and it has another kind of a resonance with the sun. It tends to rotate 3 times for every 2 trips around the sun. So a Mercurian day then is about 59 Earth days. So you have 3 of these. 3 times 59 is approximately 2 times 88. Okay, and so that's how long a day is on Mercury. Now, a lot of the questions that I may be asking you about the planets can be turned into either multiple choice or matching types of questions. And one of the main things that I might try to emphasize are the defining features of each planet. And so what is it that's memorable about each of the planets? And so one of the things about Mercury, well, it's the fastest planet. It moves the fastest. So this is where Kepler's laws could still come into play on the second midterm. Remember, Kepler's third law tells us that T squared equals Ka cubed. And so the distance A, the average distance of Mercury from the Sun, is only 0.4 AU. Okay? And so it has the smallest A, and so therefore it's got the lowest period. But the lowest period means the fastest speed, okay, because it takes the least time to go around once. Okay? And also remember that orbital motion is a balance between inertia and gravity. And so if you're in closer, you're going to feel more gravity, so you have to have more sideways motion to compensate for more gravity. You have more falling motion because you're closer in, and so you have to be moving faster in the tangential direction to keep from falling into the Sun. And so that's the reason why Mercury is the fastest planet. With the least amount of time that it takes for the planet to go around the Sun once. Another thing that we can remember about Mercury is that it has the biggest temperature differences. In the solar system. Not the highest temperature, which surprisingly actually goes to Venus, which is farther out than Mercury. But it has the biggest temperature differences. And so if you're on the side of Mercury that faces toward the Sun at only 4 astronomical units away, the day side can get all the way up to 700 degrees Fahrenheit or more even. You can get higher than this. But that's a commonly used number for the typical temperature on the daytime side. Whereas on the night side, 300 below zero. So that's quite a difference between the day side and the night side. And so this means then that we have a temperature difference of 1,000 degrees Fahrenheit. So you might wonder, well, how does it cool off so much? If it's that hot on the daytime side, how can it get so cold on the nighttime side? And the reason is that there's no atmosphere, or very little atmosphere. There's a little more atmosphere than on the Moon, but only about 100,000th of the atmosphere on the Earth, so barely even worth mentioning. And it's the atmosphere that holds in the heat. So when we go from the daytime side, you're getting that direct, very intense radiation from the Sun. You wake up a nice Mercurian morning oh, this is wonderful, and just feel the sun. It would turn you to ashes in seconds. That's how hot it is. But then by the time you get around to the nighttime side, it gets super freezing cold because there's no atmosphere to hold in the heat. And then you have this middle zone here where you could land a rocket, kind of in the transition between the daytime side and the nighttime side. And then this middle zone, which is narrow, you could pick your own temperature, maybe 70 degrees Fahrenheit. Perfect temperature. So you could land a spaceship there. You could make observations, and as far as I know, this is just my idea, and you can steal it if you want to. But I was thinking, why not land a rocket ship in that shadow zone and have it move about, what, 10 miles a day, or however much it needs to stay in the shadow zone as Mercury very slowly turns on its axis. Only one day is 59 Earth days. So as long as you could keep moving, you could stay in the shadow zone and you could explore the entire surface of the planet. And you'd be just staying right in the shadow zone the whole time. So that could be a cool thing to do. Of course, you might be in trouble if you like hit a big crater or something, gets in your way, you hit a rock, or you have a mechanical failure, and then all of a sudden you either get super freezing cold or super, super hot. But then maybe you could just blast off and leave. But anyway, this is the reason then why Mercury's got such a huge difference between the daytime side and the nighttime side, is that there's very little atmosphere to hold in the heat. Mercury looks a lot like the Earth's moon, and so the things that we would be reminded of when we look at Mercury are the heavy craters. Now, this heavy cratering comes, even heavier cratering, by the way, than on our moon. You actually have to be a kind of a trained astronomer to be able to tell the difference between these two pictures and see which one is our own moon and which one is Mercury. But there's even more craters on Mercury than on the moon. And also larger. And the reason for this, one, is that Mercury has more gravity than the moon does, and so asteroids would get moving faster before they hit the surface. It's a little bigger than the moon. The moon is only 1/4 the radius of the Earth, and Mercury is 1/3 the radius of the Earth. So it would capture more asteroids and speed them up more. But it turns out that's not the only reason. There's also the fact that Mercury can get in the line of fire of the sun. So imagine Mercury then is in its orbit here around the sun, and here's an asteroid that's falling in toward the sun. And then poor little Mercury just happens to get in the line of fire. Wow! Gets clobbered by an object that's falling in toward the sun. So that can really create a big crater. Now, if we look back up at the data projector, we can see that there are some other smaller differences. Here we see big craters. This is 100 kilometers across, which is 60 miles across. And the surface is peppered with these kinds of things. But what we also see here are these little ridges. And we don't see things like this on our moon. And so these little ridge areas, little cliffs, are called scarps. And these scarps are caused by the fact that Mercury is actually shrinking. So the surface of Mercury then experiences stress fractures. This is a geology term, but it basically means ridges on Mercury's surface. This is due to the cooling of the interior. So here's the interior of Mercury. So it's got that big core, remember? And that big core starts out hot, but then it starts to cool off. As it cools off, it shrinks. So as the surface of the core shrinks, goes down to a smaller size, then on the surface has to basically drop down to accommodate this. And so this is the accommodation that's happening at the surface from the stress fracturing to compensate for the fact that the interior is getting cooler. So the surface drops, and that leaves ridges or scarps. So here would be the ridge that would be associated then with the surface dropping down due to one of these stress fractures. Okay, now a lot of times Mercury is called the forgotten planet. And the reason is that scientists are afraid to point a telescope at Mercury for fear that they'll accidentally point it at the sun. And Mercury is close to the sun. And so therefore it would be easy to make a mistake, and that would be the end of your career if you were an astronomer. If you pointed one of those billion-dollar telescopes at the sun and blew out the reflecting mirror. So surprisingly, we know more about planets that are much farther away from us than Mercury, just because of the fact that we are hesitant to want to take a lot of chances with our telescopes. And so here's the perspective of that then. Here, if this is the sun, this is the orbit of Mercury, and then this is the Earth's orbit like this, then you point the telescope at the sun or you point it at Mercury, and the angle here is very small. So that means that you have just a little bit of a variation. Whereas if you're Venus, you've got a much bigger variation, much easier to photograph Venus with a telescope than Mercury. And so Mercury isn't always visible because of this fact. A lot of times Mercury is either behind the sun or in front of the sun. And so often Mercury, not visible. When it is visible either just before sunrise or just after sunset. Okay, one last thing I wanted to mention about Mercury before we move on, I'll go over to this left board for that, is the ellipticity of its orbit. Mercury's orbit is very elliptical. Even more elliptical than the Martian orbit. Whereas when we talked about Venus and Earth, we said that those orbits were fairly circular. Mercury's orbit around the Sun, if we go back to Kepler's law again, at its minimum distance away is only about 0.29 AU, and at its farthest distance is about 0.49 AU. So the average distance A is about 0.4 AU. But it actually comes in as close as 0.29 AU and out almost as far as half an AU. Okay? And so what this means then is with a very elliptical orbit, it is more susceptible to gravitational influences from other objects in the solar system and can destabilize the orbit. And so when we look at the orbits of planets, the computer can predict what's going on with those orbits, sometimes out past 1 million years or more. But with Mercury, you can't do it that well because this creates instabilities. And so it is possible, although this is not considered to be number one on our list of worries, that in a few billion years it's been estimated that there could be as much as a 5% chance that Mercury's orbit will completely destabilize. And if it does, that means that you'd have like a chain reaction that would disrupt all the rest of the planets in the inner solar system. And if it is in fact the Earth that hit Mercury that first time around and knocked its mantle off, then it might be time for Mercury to get its revenge. Okay? And so these instabilities in the orbit then can cause Mercury's orbit to deteriorate. So the computer simulations give us about a 5% chance. The way that they do this kind of a calculation, since it is very unstable and involves principles of chaos, is that they just change the initial conditions slightly and they run the computer program again. And they change the initial conditions. It's kind of like what they do with the weather. The weather, you change the initial conditions, you run it through and you see how many sunny days you get versus how many rainy days in your 3-day forecast. And so they can do the same thing then with Mercury's orbit, and they find that in about maybe one time in 20, Mercury orbit destabilizes when you change those initial conditions by just a slight amount. And so this gives us a way of estimating, but it's very reliable in terms of being sure that we've got it right, in just the same way that predicting the weather is not reliable. But it gives you a feeling for what could happen. And so there's maybe a 5% chance that Mercury could disrupt the whole inner solar system in the future. But this would be the distant future. And isn't likely to happen anytime soon.